Have you ever stood near railroad tracks as a freight train passed by and felt the ground shake beneath your feet? The rumble is so powerful, it vibrates through your chest. Hundreds of loaded cars stretching beyond sight, each one heavier than a house. And pulling all of that weight is a single locomotive at the front. How does one machine generate enough force to move what seems impossible? Where does that power actually come from? And how is it transferred to the rails without the wheels simply spinning in place? In this video, we'll break down that engineering puzzle step by step. At first glance, a locomotive seems deceptively simple. It rolls along the tracks, pulling cargo behind it. But in reality, it performs one of the most demanding mechanical tasks in transportation. It must convert fuel into motion while maintaining traction on a contact patch no larger than a coin. The locomotive is not just an engine on wheels. It is a mobile power plant, a precision traction system, and a sophisticated control platform all combined into one machine. Everything about its design exists to solve a single challenge. How do you move massive weight using only the friction between steel wheels and steel rails? For a long time, steam locomotives dominated railroads. They were powerful, but also inefficient. Coal had to be shoveled continuously. Water needed constant replenishment. Thermal efficiency was poor and maintenance was labor-intensive. The real limitation was not the steam engine itself, but how power was delivered to the wheels. Mechanical drive rods connected the pistons directly to the wheels. This created violent forces, high wear, and limited control. If too much power was applied, the wheels would slip. If the train needed to slow down, only friction brakes were available, and they wore out quickly under extreme loads. The solution is the diesel-electric system. When a diesel engine is coupled with electric traction motors, a completely different kind of control becomes possible. The diesel engine does not drive the wheels directly. Instead, it powers a massive generator that produces electricity. That electricity flows to traction motors mounted on each axle. These motors convert electrical energy into rotational force with extraordinary precision. Speed, torque, and power delivery can all be adjusted electronically in real time. This gives the engineer complete control over traction, even when pulling weights that would have destroyed older mechanical systems. The source of all this power is the prime mover, a large diesel engine typically producing between 3,000 and 6,000 horsepower. Unlike a car engine, it runs at a constant optimal speed regardless of train velocity. The engine's sole job is to spin the main alternator as efficiently as possible. That alternator generates three-phase AC power, which is then converted to DC current and fed to the traction motors. By keeping the engine at its most efficient operating point, fuel consumption is minimized and reliability is maximized. The engine does not speed up or slow down with the train. It simply maintains steady power output while the electrical system does the rest. Each axle on a locomotive is equipped with its own traction motor. These are series wound DC motors specifically designed for high starting torque. When the train is stationary or moving slowly, maximum torque is needed. The traction motors provide exactly that. As speed increases, the electrical characteristics of the motor naturally shift to favor higher revolutions per minute over torque. This matches the operational needs of a train perfectly. Heavy pulling at low speeds transitions smoothly into sustained movement at higher velocities. The motors are geared to the axles through reduction gears, amplifying torque even further and ensuring that rotational force is transmitted efficiently to the wheels. But how do you stop a machine weighing hundreds of tons, especially when it is pulling a train that might stretch for over a mile? Traditional friction brakes alone would overheat and fail. That is why modern locomotives use dynamic braking as the primary method of deceleration. When the engineer moves the throttle into braking mode, the traction motors reverse their function. Instead of consuming electricity to create motion, they become generators. The spinning wheels drive the motors, which now produce electrical current. That current is dissipated as heat through large resistor grids mounted on the roof of the locomotive. The energy of motion is converted into heat and released into the air. This allows the train to slow down smoothly without wearing out brake shoes or wheels. A single locomotive can pull impressive loads, but the heaviest trains require more. In those cases, multiple locomotives are used together in a configuration called distributed power. Additional locomotives are placed not only at the front, but also in the middle and at the rear of the train. All of them are controlled remotely by the lead engineer using radio signals transmitted through specialized onboard computer systems. This system does more than just add horsepower. It distributes pulling and braking forces along the entire length of the train, reducing stress on couplers and preventing the accordion effect that can occur during acceleration or braking. The coordination between locomotive units must be precise, with each locomotive responding to commands within milliseconds. The result is smoother operation, better fuel efficiency, and the ability to handle trains exceeding 15,000 tons on a single consist. One of the most critical and often overlooked systems on a locomotive is the sand delivery mechanism. No matter how powerful the engine or how sophisticated the electrical system, none of it matters if the wheels cannot grip the rails. Steel-on-steel contact has very low friction. On wet, oily, or leaf-covered rails, traction can drop to nearly zero. When wheel slip is detected, pressurized air releases a controlled amount of sand directly in front of the driving wheels. The sand increases friction just enough to restore grip without causing damage. This simple system is the difference between a train that moves and one that sits helpless with spinning wheels. Operating a locomotive is not only a mechanical challenge, but also a test of coordination and judgment. Modern freight trains can have over 100 cars and weigh more than 14,000 tons. Stopping distances can exceed a mile. The engineer must anticipate grades, curves, and track conditions far ahead. Throttle and brake applications must be smooth and gradual. Any sudden input will cause slack action, a violent snapping motion that can break couplers or derail cars. Advanced systems now assist with this. Cruise control maintains set speeds. Automatic train operation can handle certain routes. Positive train control prevents collisions and overspeed conditions. But the ultimate responsibility still rests with the engineer, who must understand the physics of the machine and the limitations of the track. Despite their very similar appearance, there is no single universal locomotive. Each type is designed for specific operational needs. Road freight locomotives prioritize fuel efficiency and long-distance reliability. Yard switchers emphasize low-speed maneuverability and visibility. Passenger locomotives focus on rapid acceleration and smooth, high-speed operation. Heavy-haul mining locomotives are built for extreme torque and continuous maximum load operation in harsh environments. Choosing the wrong type of locomotive leads not only to poor performance, but also to excessive fuel consumption, increased maintenance costs, and potential safety risks. Modern locomotives are sophisticated machines with costs that reflect their complexity. Entry-level switcher locomotives start around $1.5 million. Standard road freight units range from $2 million to $3 million, depending on horsepower and features. High-horsepower heavy-haul locomotives can exceed $4 million. Passenger locomotives with advanced traction control, crash-worthy designs, and high-speed capability often cost between $4 and $6 million. Specialized mining or industrial units can go higher depending on customization and operational requirements. A modern diesel-electric locomotive is more than just a powerful machine. It represents a careful balance between mechanical strength, electrical precision, and operational intelligence. A good locomotive converts fuel into motion with minimal waste, operates reliably across thousands of miles, and gives its crew the tools they need to move freight safely and efficiently. The next time you see a freight train rolling past, remember that what looks like simple movement is actually a sophisticated dance of physics, engineering, and human skill working together to move the economy itself.